Hi everyone, welcome back. We're going to get started with our afternoon session, so if everyone could find a seat. Our first speaker is Iain Murray. So he is a reader in machine learning at the University of Edinburgh. He works on probabilistic models of high-dimensional data and methods for Bayesian inference, and is one of the program chairs for iClear 2018, the deep learning meeting. So let's welcome Iain.
Hey, thanks very much. It's great to be here. Sorry, give me a moment. Is this thing already on?
Yeah, it's just for the recording.
Yep. Okay, it's great to be here. Thanks very much for the invite. So I kind of like to sense the temperature of the room. Who here considers themselves to be a member of the machine learning community? You're sort of machine learners, okay. And who considers themselves to be sort of a member of physical sciences, physics, sort of? Okay, and there's some overlap there, which is great. So half and half. So part of what I'm doing is sort of wanting to say there's this really cool machine learning technology that you can drop into your physics pipelines, but also you've got to be a bit careful with some of it. That's both a warning and an opportunity. It's a warning so you don't shoot yourself in the foot using things that don't work, but it's also an opportunity because you can convince the machine learning people that there's new interesting research to do to like make their stuff work. So I talk to cosmologists a lot, and this is sort of a typical figure that you might get in a cosmology inference paper saying, here is what we believe about a couple of free parameters in a cosmological model. So there are these standard models like lambda CDM and their extensions where you have maybe 7 free parameters, maybe more, saying what sort of matter there was in the universe at the beginning and then what forces there were that made it evolve. So here are the posterior beliefs about a couple of these parameters as a result of different experiments. And at least the cosmologists I talk to are very keen at having the whole sort of uncertainty so you can understand how the constraints from the different experiments intersect. So if you look at like the green band, from that combination of data, you have no idea what either of the parameters are, but you do have a constraint. And when you intersect that with the beliefs from another experiment, you end up sort of narrowing down a small ball of where the parameters are. So to create this sort of figure, you need to do Bayesian inference and you need to use inference algorithms. And I was in the approximate Bayesian inference workshop this morning, and this is what they had to say about how approximate Bayesian inference is done. They said the two dominant ways of doing it are variational methods. There's been an explosion of stochastic variational inference in the last few years in machine learning, and also Monte Carlo methods, which are the much more traditional conservative way of doing inference that sort of the statistics community has used. So who's here uses Monte Carlo methods or has used Monte Carlo methods? Yeah, like a bunch of you. How many of you have seen this paper that Monte Carlo is fundamentally unsound? Like 2 of you. Okay. The rest of you should read this paper. Like, aren't you worried? So I did my PhD in Monte Carlo methods, and this was sort of an interesting thing I looked at. It's a fun read. Tony O'Hagan is sort of a Bayesian fundamentalist, and so anything that isn't sort of really rigorously sound and the correct way of doing things, he'll argue about vociferously. He has sort of a couple of objections. So here's a like textbook figure of how Monte Carlo works. You can see in the middle that we've sampled these points along the x-axis, and then we evaluate the function that we're integrating and the distribution that we're getting our integral with respect to. And you can see there's a couple of points right next to each other. So one of his objections is you haven't learned anything new about the function. The thing you're computing is just this deterministic integral, and when you evaluate something in the same place twice, you don't know anything new, so it's kind of crazy that your estimator changes. So really he thinks if you're evaluating expensive functions and the function here is expensive, then you should be treating your computation more carefully. Here's sort of another objection that I have to the cosmological standard practice. So textbook method Metropolis Hastings, this is widely used in the pipelines to create this sort of figure. So They might use slightly cleverer algorithms, but the basic idea is the same, that you're taking some walk through the parameter space. So this is through the 7-dimensional space of cosmological parameters. And the algorithms will do things like propose some move and say, okay, I'm now going to stall for a few seconds to do a computation that inside is doing a lot of clever surrogate modeling to compute a surrogate likelihood cheaply. And then I'll decide to take that move. I'll do another proposal. I'll stall for another few seconds, maybe minutes if you're more careful, and then go, no, I'm not going to do that. And you've done all this computation just to make a binary decision to say, actually, I'm not going to do anything, and I'm going to go somewhere else. And maybe we should be using all of the computation we're doing to sort of learn stuff about the surface and be a bit more efficient. So there's an old idea in the machine learning community that I think is massively underused and should be used more. And the term recognition networks came in sort of early papers on the wake-sleep algorithm. It's sort of from within machine learning. But it's a simple idea. So if you had a parameter that you sample from the prior, so I could make up 7 cosmological parameters. You then could simulate data. So lots of us in this room have models that we can simulate. So you simulate a data vector. For the cosmological example, this would be a matter power spectrum. So X could be a vector of 100 numbers that describes a power spectrum across the sky. And then you could just do that again. You could pick a different cosmology, create another power spectrum, and so on. And in machine learning language, you've got a training set. You've just got a bunch of power spectra and a bunch of cosmological parameters that are plausible given those. They're so plausible they're actually the ones that generated the power spectrum, but they're also sort of ones that go nicely with them. So we could play a guessing game. I could train a machine learning system on this data set, and then if you gave me a power spectrum, I could try and guess which cosmology you used to generate it with. But we know from the figure that I'm not going to do very well at that guessing game for some models. So for some models, there's a large band of parameters that could have generated any particular data set. So what we want to do is extend the guessing game to be a probabilistic guessing game where I don't guess the parameters, I give you a distribution saying, here are my beliefs about which cosmology I think you used to generate the thing. So they said recognition networks is an old idea. There was a science paper in 1995 that had it embedded within a machine learning system. Quaid Morris, more than 15 years ago, was proposing using neural networks to play these guessing games to do inference in sort of real models, like medical diagnosis models. And there's been some attention within the statistics community, but not that much. So George, who's sitting right there, and me had a NIPS paper last year where we sort of took some step towards making this idea more practical for models that you could see in physics and in other areas. And so it had this basic idea that we're going to fit a model to, given an input data set, which could be a matter power spectrum, or it could be something else, create a probability distribution over what parameters we think generated that. And so how are we going to do that? This is all really old technology. If we go back to Chris Bishop's 1995 textbook or his tech report in 94, there are neural networks that can play this sort of guessing game. So you have a neural network diagram with circles and lines, but for us, what we're going to do is in the bottom, throw in our data, like throw in a power spectrum, 100 numbers describing a bin-dot power spectrum. And the outputs of this thing aren't just a guess of the parameters, but they're the parameters of a distribution. So it sketches out, here is the band that I think could contain these parameters. So in this example, they're the parameters of a mixture of Gaussians. And you train this thing so that it will put the band in the right place. Okay, so what we did in our NIPS paper was we trained this model so that for any data set, it will tell you what to believe. And then you just throw in your observed data and it tells you what to believe for that data. So there's no variational inference, there's no Monte Carlo methods, it's just this machine that directly tells you what to think. And the problem with this method, well, there's a few problems. There was a paper this year by Luckman et al. Where they point out other problems where the code fell over when they try it on their problems, and they explored alternatives. But one of the problems for simulation models is that simulations are expensive, and neural nets often use a lot of data. So, you know, if someone generically said, oh, can you fit a neural net for me? How much data do you want? I'd be like, well, as much as you can have, but tens of thousands of points would be nice, and more please if you can. And in these simulation models, every data point is expensive, and we'd like to do it with as few as possible. So the standard sort of off-the-shelf machine learning tools are a bit worrying there, and we used a Bayesian conditional density estimator to fit this thing so that we could, say, run only 100 simulations and fit a whole neural network with only 100 input-output pairs examples. So the result of that fit is that this distribution that we evaluate, the distribution over the cosmological parameters given the data, isn't going to be equal to the true posterior distribution, because we haven't worked out how the parameters relate to the data, because we've only got a bit of experience of the model. And the failure mode is that this distribution, if we are sensible, will be too broad. There'll be uncertainty in this distribution due to underlying physics, the way the data works. There's this intrinsic band of uncertainty. And there'll be additional uncertainty on top of that because we haven't figured out what's going on. So what we want to do is fit to a few simulations, get a preliminary idea of where the parameters might be, but it's broader than we'll end up doing. We can then sample from that distribution to get parameters that will be more useful to simulate again. So we're going to run more simulations by sampling from this second distribution, getting parameters, running simulations at those parameters, and then refitting our original model. And so if you're a physicist, you know, this sort of thing, I think, can be a lot more efficient than the Monte Carlo methods, and we have preliminary results showing that that can work. But if you're a machine learning person sort of interested in challenges that could be motivated from physics problems, this stuff doesn't work as well as it should do. So for example, I would like to be able to run one simulation. If this thing is really expensive, I'd like to run one simulation, get some idea of the posterior distribution given that tiny bit of information, and then go back and refit my model and then run one more simulation again. And if you believe all of the Bayesian machinery and you believe all the claims of Bayesian neural networks, that should work. And the practice is it doesn't. Our approximate Bayesian neural networks don't work well enough to sort of really treat the uncertainty inside them seriously when you have tiny, tiny data sets, like data sets of size 1. So there's real opportunity here to sort of get interesting problems from the physical sciences and motivate convincing people at NIPS to work harder on these neural nets. Okay, I think it's really important to spend time talking about the ways that these things are going to get things wrong in workshops. So when we publish papers, you know, we've got to say, I bet my method is better than the method from last year. Whereas I don't have a paper to publish here, so I can say whatever I like. So what will happen when you make predictions with these things when they can't quite fit things? So let's imagine that these magenta points are sampled from the true posterior given some particular data set. So I've observed a power spectrum. If I had infinite compute resource, I could compute a posterior and they'd come from this slightly artificial looking thing. Then in practice, what will happen is if I use neural nets, I will underfit things. It might be because I've assumed the posterior is Gaussian, in which case I'll fit the ellipse I've shown. That's the maximum likelihood ellipse. Or it might just be that I'm in high dimensions and I haven't seen enough data yet. So even if I've got a flexible density estimator, I won't have narrowed in on the distribution yet. So if you fit these things using likelihood-based methods, if you're using Bayesian neural nets or even penalized maximum likelihood, this is what you'll do. You will slap a vague distribution down and not narrow in on all the structure. So if I sample from this Gaussian fit, I get points all over the place. I get points in regions where those parameters are actually ruled out by the data. I just haven't figured it out yet. So the failure mode is I'm going to be too broad in my beliefs. I am assigning too small probability to some of these outlying points, but the cost function, the KL cost function you fit when you do maximum likelihood, doesn't assign those 0 probability. It doesn't completely rule them out. So for parameter inference in cosmology, I think this is the right failure mode. If I don't have enough compute resource and I can't figure things out, I'll just come to vague conclusions. I won't say, oh, there's no way that omega m is smaller than this value, and then it is. That would be embarrassing. And that's not true of all machine learning methods. So if you went away and did a variational method, the variational cost function would really hate this sort of solution where you're putting probability mass in impossible places. So if you did variational inference, you would get predictions which hug inside some part of this distribution, and it would rule out some parameters spuriously. It would say, oh, there's no way you're in this arm over here, when you could be. And I worry that most GANs could do something fairly similar. So if you generate points in a void where the real system would never do that, a discriminator can latch onto that and say, okay, here you are generating points from the wrong system, you're wrong. And it will encourage you to hide inside the bulk, the biggest, easiest part of the distribution to capture, and you might end up running things out unless you're very careful about adding on sort of extensions to the GAN. But I think the default method would be a bit dangerous. And so I worry when I see people reading the shiny NIPS paper, and if there's really good code available, they might apply it without thinking through whether it's actually a good idea. And of course, there are people here like very special casing their methods for physics, which is great. Okay, so I've got 3 stories. I'm interested in doing Bayesian inference for these problems, and there are 3 parts in Bayes' rule. This is sort of the posterior and the prior and the likelihood. So I've so far said, can we get neural nets to just do everything for us? We're going to say, this is what I want. I want the posterior over the parameters given data, and we'll train a system to just do that directly. And I found that hard to sell to collaborators because often they're doing multiple analyses and they want to reuse fits more than once. And so it can make sense to split up the problem and model separate parts of it. And it's useful to go in and say again, like, what are the failure modes when things go wrong when you model the different parts? What are the appropriate tools? What are the tools that are maybe less appropriate? So I've got a story about modeling the prior of a system, which I liked that I'm telling you here because it came about from a conversation with Phil Marshall at a NIPS workshop a few years ago. So Phil Marshall was here for a sort of astronomy and machine learning workshop, and in the bar afterwards he said, oh, I've got this statistical problem and I think you can help. So they had this sort of proof of concept paper in AppJ about measuring the mass of the Milky Way. So there's a galaxy we live in, and there are these small puffy clouds, Magellanic clouds, which are orbiting around the Milky Way. And they had this paper where they said, if you observe the positions and velocities of the Magellanic clouds, these things that are orbiting around us, you can use those observations to infer the mass of the Milky Way, which is probably dominated by dark matter that we can't see. So they're Bayesians, like all good people are. So they wrote down Bayes' rule, and they said what we're doing is inferring a vector x, which is the properties of the Milky Way and its companions. So this vector contains m, the mass of the Milky Way, and it contains the positions and velocities of these companions. And we're going to try and infer that from noisy observations of the positions and velocities of the companions. So we don't have any direct measurement of the mass. We've got these indirect observations. And the likelihood here tells us precisely nothing about the mass of the Milky Way. The likelihood just says, how do these noisy observations work? And the only thing that tells us about the mass is prior physics knowledge that says the mass of this thing is related to the orbital dynamics of things that go around it. So they had access to this big simulation, the Bolshoi simulation, where you simulate gravity in a big box, look at synthetic galaxies and look at the properties of those galaxies. So here's a scatter plot of the properties of loads of simulated galaxies. You don't need to be able to read this. In the bottom right, there is a histogram of the masses of the galaxies in the simulation, and the other properties are the speeds and positions of the Magellanic Clouds, or the two companions that the synthetic galaxies happen to have. So what they're going to do is use this knowledge encoded in the simulation to infer properties of the Milky Way. And the way they did it in their paper was they used importance sampling. They said, we've got a bunch of samples from the prior, that's step one of importance sampling. We're going to look at how much they're like the Milky Way. So we're going to attach a likelihood. If the simulated galaxy doesn't have two large companions orbiting around it, it's obviously not like the Milky Way, so we'll give it a weight of 0 and ignore it. And if it does have two companions, and they're moving at similar speeds to ours, and they're similar distances away, then it might be like the Milky Way, and so we'll give it a large weight. And then we'll look at the weighted samples. So this is a figure from their paper. This black line is, roughly speaking, a histogram of the simulated galaxies that look like the Milky Way. And so that is my beliefs of the mass of the Milky Way, because it's a histogram of the masses of these simulated galaxies. So they started with 2 million galaxies. Almost all of those were thrown away immediately because they didn't happen to have exactly two companions like we do. They then had 40,000 with two companions, of which 400 were vaguely like us. The speeds and velocities were within the error bars of the observations. So what Phil Marshall said to me is, can we get more samples? Because we've really only got about 400 samples here, and that Bolshoi simulation, which wasn't run for this project, took 2 years of supercompute time, so we're not going to get another one of them. So could you somehow use magic machine learning to give us more samples? And I think if GANs had been trendy at the time, I'd have probably been, oh yes, because GANs can generate more samples. But fortunately, they weren't invented yet. So I thought I'll do density estimation. So I've got this simulated data. I'm in a 7-dimensional space. These are 7-dimensional vectors describing galaxies. The baseline thing to do is I could just slap an elliptical ball on top of those points and fit them with a Gaussian and say that's my prior. That's like one line of code, so I did that. And then I could go, oh, well, there's spiky things in this density. Maybe I won't get away with that. I'll fit a mixture of Gaussians. And then because I had code kicking around for it, I could fit a neural net density estimator. So if I fit these models, I can draw samples from them and look at whether they're good. So here are a bunch of samples from the mixture of Gaussians. Here's the original simulations. Mixture of Gaussians, original simulations. So the mixture of Gaussians is blurring out the true distribution. It's quite hard to model this spiky, truncated distribution with a load of rugby balls or American footballs. And so things are going to go wrong there. We're not going to rule out things that actually the theory tells us can't happen. And then when we fit the neural nets, we get a much better fit. So here are simulations. These are the extra samples I generated from the neural net. Here were the original ones, the neural net ones, and the distribution's a lot closer. But it's still going to have the failure mode that I'm slightly blurring things out because that's the cost function that I'm fitting. So what I can do is take that prior, and now I've got a density I can evaluate because I've got a fit to what the simulations do, and push it through Bayesian inference. And I just used importance sampling. I didn't need to do anything complicated after that to create this plot. So the gray line is the beliefs about the mass of the Milky Way if your prior is this ellipsoidal ball that loses all of the structure that's in our model. And as you hone in on the structure, the black dashed line is a mixture of Gaussians. You're a bit more confident about the mass. And the magenta line, you're more confident again. And to the sort of more theory people in the machine learning community, we desperately need some theory here. So I have some hand-waving intuition that the cost function I'm fitting means that I won't overfit because I'm being careful about my model comparison. And I'd like to make a claim that I'm not ruling out, that there's no way I'm ruling out the true mass of the Milky Way here. I'm getting tighter beliefs because I'm capturing my prior better. If I were fitting a standard GAN, I would really worry that I'm cutting off bits of this distribution and I might have just thrown away the true mass. And I don't think I've done that, but I don't have a proof for you, and that's embarrassing. Okay, so the third little bit of the story is like, what else have we got? So we can model the prior. That's just a fixed distribution. We can use mixtures of Gaussians for it. We don't need neural nets necessarily. We can also model other parts of the equation. So here's a cartoon picture I stole from George, which will motivate why you might want to do something else. So here's a data analysis problem where you get time series. So you might have a model that contains a bunch of differential equations you could simulate. It could be a systems biology model. Oh, we're in a physical science workshop. It could be a something else model, that your favorite model with differential equations in it, or a queuing model, and you observe these time series, and then what we want is this posterior distribution, some posterior distribution over the parameters in our model that explain these data. And we could try and just learn the posterior directly. We could get a neural net that absorbs this data, but because there are multiple realizations of the data, we'd have to do something like use some pooling operation or a recurrent net or something that can chew it up multiple observations. It would be more complicated. And this posterior contains sort of weird thresholded bits. It might be harder to fit the parameters than over here. This data looks really easy to model. It's like these really boring curves with about one kink in them. I think I could probably write some sort of surrogate model that would behave in a similar way. So the naive thing to do is to say what we could do is model this likelihood term, the probability of x given theta. We could create a neural net that you give it parameters, and then it spits out an example curve and says, here is a sample data point that could come from this model. And then if we had a surrogate model, we would know that probability, and the posterior would be easy to compute, and we could run a standard inference method on top. And if you get, say, some neural net code from George's webpage or my webpage and run it on this problem, you'll probably get embarrassingly wrong answers. So the sort of thing that could happen if you model the time series is you won't model them exactly. Unless you have infinite data, you won't fit it exactly. And the way you'll make mistakes is that you'll sometimes generate time series that the real system never would have done. And that's fine if you were trying to say this is what might happen. But it will introduce weird biases on the parameters that you might not expect. And when you multiply many wrong terms together, what you'll get is some posterior distribution, and then you plot where the true parameters are, and it will just be somewhere else. So you end up saying, I'm really confident the parameters are inside this small ball over here, and then they're not. And that's just really embarrassing, because then like your physical science collaborators would never trust you again, because they publish this paper saying, oh, this is our predictions, and then a new experiment comes out showing they're wrong. So what you'd need to do is something that takes into account how we're actually going to use the surrogate fit. We care about the likelihood surface or the surface of the posterior. So I put here a link to a paper from people in this room where they're looking at a more sensible cost function than the one I specified, because they're looking at the ratio of the likelihood at different parameter settings, and I think that's the sort of thing you'd have to put in if you wanted to get correct answers. Okay, so I've probably run a bit under time, but I was mainly just wanting to give you a flavor of some of the ways I think surrogate models can be used in machine learning. There have been some detailed talks on sort of clever structures, recurrent models, and convolutional models this morning, and I've just zoomed out and said, you can represent distributions with neural nets, and on my webpage we have several technologies for representing distributions. You can fit distributions with hundreds or maybe thousands of variables fairly routinely if you have enough data, if you can afford to make enough simulations. And I think that these tools are really underused in the physical sciences. So if you're a physicist, I encourage you to play with these things and have a go. But if you're from the machine learning side, I think we've got to ask, why are these things not being used that much? And I don't think the main reason is I haven't evangelized them enough. I think the main reason is that we are not providing the guarantees we need to, and we need to make these things sort of a lot more robust. So I mentioned there was this paper at NIPS this year where neuroscientists took the methods that we'd sort of been working on and made it work for neuroscience, and they had to do another NIPS paper amount of work to make that happen. So we can get NIPS papers out of making these things work, and I hope we will in the next few years. Thanks.
So we have quite a bit of time for questions. Unfortunately, we don't have any microphones to go around the room, so if you just want to like say your question fairly loud, that would be great.
Yep.
High-dimensional MCMC methods work in contrast with, say, main or other tools that you have.
Okay, so the question was, how do high-dimensional MCMC methods work compared to using these neural net things like NAID to do the recognition? And that's sort of an empirical question, so I can give you experience on the things we've tried, but we need to understand that more broadly. So in our paper, we had problems with sort of a few parameters where the likelihoods were either incredibly expensive to compute or intractable. And so the MCMC alternatives involved using ABC algorithms, which can sort of be quite painful. And so there what we did was say, you will get a certain level of accuracy for a certain amount of time, and you can plot time against accuracy. And the thing with MCMC methods is that you can run them for longer, and they'll get more and more accurate. So for the classic sort of sequential Monte Carlo ABC methods, or the sort of different variants of those Monte Carlo methods, you get a trajectory, and then for sort of the neural nets, we can say, where are we on that front? And of course, because we got our paper into NIPS, in those comparisons, we did very well, and we're faster than those methods, and also you get something that you can perhaps reuse more easily than the bag of samples. You can do hybrid Monte Carlo on the parameters of a neural net. So like Radford Neal in the early 90s was getting neural nets with maybe tens of thousands of parameters and getting really good predictions. His code is written in plain C with no dependencies. It still works. Like C code doesn't rust, and you can still win competitions by getting Radford's code and using it. You couldn't use NAID to predict 10,000 parameters of a neural net, because that posterior surface is just insane, and there's no way you could represent that whole thing. You've taken this really hard inference problem, and then you're trying to use a neural net to represent something more complicated than itself. So there's clearly a dividing line where you would swap from one to the other. I think when people are doing MCMC on things with only tens or maybe hundreds of parameters, even as someone who's an MCMC enthusiast, it seems a bit icky to me. It doesn't make much sense. Okay. Okay, so there was a question there that said, when you're training neural nets, you have to decide how to terminate them in some way. You're running stochastic gradient descent. How do you know when you're done? How do you sort of monitor these things? So in theory, if you've got a Bayesian neural net and you're doing the variational objective, in theory, you would like to sort of fully optimize that. Like there's no sort of necessarily early stopping thing. But as I say, in practice, I'm not convinced that we can set the priors on these neural nets sensibly, and I'm not convinced that we've got the best approximate inference technology. And I think you would be crazy not to have held out validation sets and say, are these things ruling out parameters that we've got sort of held out? And you have to do that sort of monitoring. All of that machinery, the sort of the Bayesian machinery, was really just used to guide our simulations and to get results that we sort of really believed at the end. Once we've narrowed down the region of parameters we think are plausible, we informally simulated the hell out of it to like make sure that you can pin down what's going on there. And I think we'd like to sort of go a bit further so that when the simulations are really, really expensive, we don't have to sort of do a ridiculous amount to be safe.
An alternative to Markov, Monte Carlo method, stochastic method would be deterministic method, right? And then not only variational traditional standard like near field, but probably belief propagation and things like that. There are multiple extensions. They all use structure, which is, well, have a lot in physical properties. Can you comment on that, on the use of those alternatives?
Okay, great. So the question is that I mentioned variational methods and Monte Carlo methods and evangelized neural nets, but there's a wider family of approximate inference methods, and message passing methods like belief propagation was mentioned. In fact, when I first came to NIPS in 2002, loopy belief propagation was the thing. That's what everyone was doing. And someone literally said to me, I think machine learning will be over soon because we can write down all these flexible models and loopy belief propagation will solve them all. Which didn't happen, by the way, in case you hadn't noticed. So yes, there are wider things. And I think like Microsoft's infer.net framework is really nice for that it embodies these message passing algorithms and encourages you to specify the structure of your model and work out intermediate things. What I'm suggesting here is this really brute force thing where I say there's these parameters at the top of the model, then all sorts of stuff happens in the middle, and I don't want to have to talk about that because it's sort of this whole simulation of gravity and creation of the universe is a nuisance process I don't really care about. I only care about seeing the power spectrum at the end, and I'm going to directly leapfrog over everything that happened in the middle with no structure. And that's either a good thing or a bad thing. I don't have to make lots of assumptions. These things are relatively low dimension, like 7 parameters, 100, and I don't need that complicated an object to represent them, but I'm throwing away knowledge that we actually have, and that's a trade-off. And I think I probably can't argue too strongly for one or the other right now.
I think we have time for one more question.
You pick.
So you talked about how it would be nice to have theory to give some sort of guarantees, and I agree with that. There's a lower hanging fruit, which is to somehow try to provide diagnostics about if it is failing. I was just wondering if you could comment about what kinds of diagnostics that maybe are available prior to it.
Excellent question. So the question is that I was saying that we need theory inspired by the sort of rigor police that have been patrolling around NIPS, but the first thing that we need is sort of diagnostics so that we can sort of intuitively see whether things are going wrong, perhaps some signal as to what they're going wrong with. So the paper that George Theo and I have at NIPS this year, one of the inspirations for that was precisely that if you've got a neural density estimation model, there are ways of doing model checking on it, which both tell you when things are going wrong and provide a mechanism for you to fix up the model. So one way to do model checking in these probabilistic models is to say, to generate the data you've got, you'd need to use certain random numbers. What do those random numbers look like, and can you see pathologies in them? But Gelman's Bayesian statistics book has a whole load of other ways of doing model checking, and we could think a bit more creatively about how they'd apply to these neural models as well.
Let's thank Iain again.